So we're taking a look at this image where we have stair steps and ramps. Each figure is labeled A through F. And so the first question is, which one of these figures do you think is the most steep or the steepest? So we all agree that C is definitely the most steep on this page. So the follow-up question is, which one of these would you say is the least steep? In my previous classes today, it's kind of been a toss-up between A, D, and some people thought F was, the least steep. It's kind of hard to tell between like A, D, even F. We don't exactly, maybe can't put that in words or come up with an exact value. And that's what leads us into our learning for today. And so in mathematics, it's important that we can not just say like, oh, this is more steep, this is less steep. It kind of just feels more steep or less steep. We want to actually be able to assign like a numerical value and say how steep something is, maybe with a number, or identify. We should be able to go through each of these figures and put them in order of most steep to least steep. And we will be able to come back and probably do that tomorrow after we learn a little bit more about what this is called, which is slope. So your page should look like this. If your page is blank and you're copying these down on paper, the first thing that you must write down is the title here. It's really important that you have the title because we all know what happens. You don't submit it. I'm like, hey, where is this? And you're like, oh, I know I submitted it. And then you can't find it because you just wrote it on some random piece of paper. Put the title down so you can find it. It's 3.3 guided notes, rate of change and slope. Make sure you have that written down. And then these definitions here are also going to be important. They must be written down. So the first one is rate of change. Rate of change tells how a quantity is changing over time. Remember, a quantity is a numerical value. It's like a number. So how a quantity is changing over time. We looked at a lot of examples of rate of change last week when we did those graphing stories on Thursday. In the Desmos activity, we watched some videos and we saw how things were changing over time. And then in the later activity, I gave you some graphs to look at and you described what was changing and happening over time. So rate of change, I mean, we saw all different kinds of things happening with those stories. Change can happen, values can increase, values can decrease, values can remain constant. We saw all of those in our stories. We saw even some stuff like this. But if we're looking at a particular line or a point to point, slope describes the steepness of that line. So you also need to write this down if you're taking your notes by hand. So if we're talking about how steep something is, that's the slope. And that's what we just looked at with those ramps and staircases. So make sure you have those definitions clearly written down. And then if you're writing by hand, you are going to kind of make a table. So I want you to title scenario, graph, and slope. But I'm not going to make you write every single thing down. I'll show you exactly what to write down. So write those titles down, scenario, graph, and slope. And then we're going to do example 1. So you can write number 1. And situation number 1 says, Tyler is training for a half marathon. Yesterday, he ran 6 miles in 53 minutes. If you're writing these by hand, if you want to write everything down, you can, or you can just write Tyler ran 6 miles in 53 minutes. That's the most important thing. So that's the scenario. So now we're going to graph it. And just like on Thursday, I'm not so worried about specific points, but we just want to get the general idea of this graph. So let's take a look at what we have here. I have time on the x-axis. And in this situation, what unit are we using for time? Minutes. And a follow-up question, I've got to get up to 53, so what should I count by on my x-axis? Tens or fives, I'm just going to count by tens to make it easy. 10, 20, 30, 40, 50, 60. Gotta squeeze them in there, but we'll count by tens. And then distance, it already tells us we're measuring in miles. There's 6 miles, so I'll just count by ones. All right, so just like we did last week, we always want to kind of consider also where our starting point is. So if Tyler is going for a run, at time 0, at 0 minutes into his run, how far has he traveled? Nowhere. You're right. Nowhere. So distance 0. So our starting point here is 0, 0. At time 0, he's ran distance 0. Now, I don't know anything else about Tyler's run. I don't know if he ran consistently, the same rate the entire time. I don't know if he started and stopped or got faster or slower. All I know is that at minute 53, he had finished 6 miles. So I'm going to go over to 53 minutes, which is just past 50, and I'm going to go up to 6, and I'm going to plot my point here. Here we have 2 points. Anytime we have 2 points, it doesn't matter how they're situated. If I were to connect 2 points together, what shape would I be creating? A line. Awesome. So if we connect these 2 dots, we have a line. And if we have a line, we have a slope, because that line has a certain steepness. So we want to kind of talk about or describe the slope of this line. And I'm not so concerned about like how steep it is, but I'm more concerned about like the direction of this line. How could we describe the direction of this line? It's increasing. Increasing means it's going up, right? And if we have a line that is increasing or moving up, if we're reading it from left to right, we say that this has a positive slope. So you definitely need to have that written down. So that is slope option number 1, positive. It goes up. Now, you don't need to write this, but it doesn't matter if he's running this fast or if he's running only this fast. All of those lines are going upward direction. So we say all of those lines are positive. It doesn't matter how steep. We'll get into how steep tomorrow, but all I'm worried about here is that they're all going up, so they're positive. Now we'll look at another scenario. So if you're writing these by hand, I want you to put a number 2. This one says, Emma is traveling to her grandma's house for Thanksgiving. She uses cruise control so that she maintains a consistent speed of 65 miles per hour. If you're writing this by hand, all you need to write is Emma maintains a consistent speed of 65 miles per hour. You can cut out the other stuff about Granny. Unless you really want to write it down, you can. You don't drive yet, so you might not know. But cruise control, like if you're going on a long trip and you're driving on the highway and you don't want to, hold down the gas the whole time, or sometimes if you're driving for a long time on the interstate, you can start to go a little too fast. So if you want to keep yourself from speeding, you can flip cruise control on, and the car itself will make sure that you're going the same speed. So the car will essentially drive for you. So that's what cruise control is. So Emma is traveling, we can assume maybe a long distance to grandma's house for Thanksgiving. And so she uses cruise control. So for this graph, we've got speed and time. Time, maybe we'll measure time here in minutes. And speed is being measured in miles per hour. So I'll maybe measure in 5-minute intervals. So I'll count by 5s here. And the speed, I've got to get all the way up to 65. So I don't want to count by 1s. I'll probably even just count by 10s. All right. So what's happening in this situation? All I know is that she's driving on cruise control. This story is not telling me when Emma started driving, how she turned her car on, how she accelerated, how she got on the highway. Basically, time is starting when she presses the cruise control button. When Emma presses cruise control, how fast is she going? So at time 0, how fast is she going? Okay, 65. She wants to go. So she gets on the highway. She's driving. She hits 65. She presses cruise control because she wants to lock in at that speed. So at time 0, when she clicks the button, she is going 65. So we'll put a dot here. At time 0, she's going 65. Well, she pressed cruise control, so the car is making sure she drives at a constant rate. So 10 minutes later, it's how fast is she going? She's still going 65. She isn't, as far as we know, nothing has changed. After 25 minutes, she's still going 65. After 35, she's still going 65. As far as we know, she's just coasting along at 65 miles per hour. So all these points are lined up and we can form a line going from left to right. So obviously this is a different kind of line. It looks different than our first example. If you had to describe this line, what would you say about it? It's flat. It's constant. You could write constant down if you want. Straight across. Okay, this is a horizontal line, right? Horizontal. Okay, so know that word horizontal if you didn't. And a line, a horizontal line that goes straight across, we call that slope 0. A horizontal line has a slope of 0. And it kind of makes sense, like if that were a sidewalk and you were walking on a flat path, and slope is steepness, it has no steepness. It's not going up, it's not going down. Slope is 0. Okay, looking at number 3, we're actually all gonna rewrite this scenario because I messed up and put the wrong situation here. I wrote a situation about someone saving money, but we need a story about someone spending money. So here's the situation. Mrs. Montgomery, we'll say Mrs. M, has, let's see, I'll say I have $85 budgeted for gas. She, I have to talk in third person. She spends $20 per week on gas. Okay, that's the main idea here. Is I've got a budget for gas and I'm spending $20 per week. So instead of saving, just cross off the word savings. These are not my savings. It's just my money. So the amount of money we're discussing here is my gas money, which is 85. So I'll count by tens. And time, we're talking about my spending per week. So I'll count time in weeks. How much money am I starting with? 85. So at time 0, at week 0, I check my bank account, my budget for gas, and I have $85. But I have to spend $20 per week. So at week 1, how much money do I have? Good, we decreased by 20. So at week 1, I have $65. After 2 weeks, how much money do I have? 45. Okay, and then we just keep going down. At 3 weeks, I go down 20 more, which would be 25. And at 4 weeks, I go down 20 more, which would be $5. And then on week 5, I cannot afford my gas anymore. Which is good, because if that's my budget for each month, then that's about perfect. All right, so because I am spending the same amount each week, I have a straight line here. So I can connect those dots and form a straight line. So looking at kind of what we've been discussing previously, how could we describe this line? It's decreasing, which means it's going down. And so if a line that's increasing and going up has a positive slope, a line that's decreasing or going down must have a what? A negative slope. We've got one more situation to discuss. And this is kind of a weird one. It's actually kind of an impossible situation, what we're going to talk about, and for a reason. But if you are writing this by hand, just go ahead and write this whole thing down. 30 minutes into working on your math test, you solved problems 1 through 14. Now, listen to what exactly is going on here. It's kind of hard for me to write because, like I said, this is kind of an impossible situation. But time, we're talking about minutes. That's my unit. And we're talking about 30 minutes. I'll count by fives. So 5, 10, 15, 20, 25, 30. And problems 1 through 14. I don't think I can reach 14 counting by 1, so I'll just count by 2s. Okay, so here's what I mean in this situation. I pass out a math test and I am timing it for whatever reason. So 5 minutes in, I walk around the classroom and you are just sitting there with your head down. You haven't even started, haven't even picked up your pencil, nothing is done. I come back around after 15 minutes. I check. You are still just sitting there, have not even picked up your pencil, nothing is done, nothing is answered. 25 minutes in, I walk around again. You are still sitting there. You have done absolutely no work, no questions answered, nothing. 29 minutes. At 29 minutes in, you still have not even touched the pencil. I look away for a second, and when I look back at you, minute 30, all of a sudden, questions 1 through 14 are all answered in a one split second. So that's what's happening here. It's kind of a weird situation. Obviously, if that happened, it would be like, obviously something sketchy is going on. But how we would graph that is, 5 minutes, nothing, 15, nothing, 25, nothing. At 30 minutes, all of a sudden, you've answered question 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. They magically all got answered in one split second. So here's our line. If we connect those dots. All right. So this line here, how could we describe this line? What's it look like? What's its direction? Okay, straight up and down. The vocab word for that is vertical. Okay. Yep, this is a vertical line. It's straight up and down. And the slope of this line is called undefined. That's why there actually is no genuine real world situation that works for this because it's undefined. It's kind of like a no solution kind of thing. It is a solution. It's undefined. And it does look like something. It looks like a vertical line, but it doesn't have no slope, zero slope, but it has an undefined slope. Whoops. Okay. So those are the 4 types of slope. A line going up has a positive slope. A line going straight across has 0 slope. A line going down has a negative slope. And a straight vertical line has an undefined slope. So that is what you need to learn for today. Tomorrow, we're going to get into how to actually assign a numerical value for the slope of a line.